Hey guys, welcome to my channel Euclid Mathematics. Today we are going to continue questions from Yemen test. So here we started in our previous lecture necessary and sufficient condition to check whether sequence of function which uniformly convergent or not. Okay. So in my today's lecture we are going to solve more example on Yemen test. Okay, which is a more important to our competitive exam like a GATE, NET, SET or multiple type of the exam. Okay, which is a more important topic from real analysis. Now here it is my example sequence of function it is given here. So in my today's lecture I'm going to explain same example which is in the context of Yemen test and in the context of the definition of uniformly convergent sequence of function. Okay, so now first of all solve our example by using Yemen test. Okay, so we know that in our Yemen test we find first of all the value for fx. Okay, when we apply limit n tends to fn x we get the fx. Okay, so here it is our sequence of function and x is from the real number. Okay, so fx it is here limit n tends to infinity fn x. Okay, so when we apply limit n tends to infinity fx, so we get the 0. Okay, so for to check this one you can take n common from here, so n get cancelled with that n. Okay, so numerator, if n is not present in numerator, that means our sequence of function it never become infinity, it gives a finite value, but if the infinity comes to denominator that means it goes to 0. So when we apply limit n tends to infinity to fn x we get the fx as a 0. Now substitute this value into our Yemen. Okay, Yemen in the term of n we have to find out. So Yemen is equal to x belongs to real modulus of fn x minus fx. Okay, now substitute the value for fn x which is a nx upon 1 plus n square x square, and fx we got the value which is a 0. Okay, so supreme of x belongs to R, keep as it is modulus. Okay, remember that one is always in a modulus. Okay, because we want the value for Yemen is a positive. Okay, so nx upon 1 plus n square x square. So by using this we cannot say anything about the value for Yemen. Okay, so we have to find out what that value gives. Okay, so consider that one as y, nx upon 1 plus n square x square. Now differentiate it as usual we do in our other example. Okay, why we have to differentiate? Because we have to find out whether this y having some fixed constant value or might be 0 or any other values. Okay, so differentiate it. So why differentiation into y dash? U by v. Apply the quotient rule of a differentiation here. U by v. Okay, v into derivative of u minus u into derivative of v upon denominator v square. Okay, then we get here the value n plus n cube x square minus 2n cube x square upon 1 plus n square x square to bracket square. Okay, so for finding this value put y dash as a 0. Why we are substituting that y dash 0? Similar case we apply in a quadratic equation. Okay, in our quadratic equation for finding the value for their constant variable we always use that equation, quadratic equation, as a 0. Okay, so similar case we have to apply here. Put y dash 0, that means this term totally getting 0, that denominator it goes to the other side, it goes to 0. Okay, so I write here n minus n cube x cube which is equal to 0. Okay, why? That denominator is goes to 0 even if it is present here, that means the value of it is 0. Okay, so that's why second step n plus n cube x square is a 0. Take n common from here, take it to the other side, it also goes to 0. Okay, so left term here 1 minus n square x cube. Okay, so take it to the other side, we get the 1 which is equal to n square x square. Okay, now find out the value for x square which is 1 upon n square, and the value for x which is a plus minus 1 by n. Okay, that plus minus 1 by n value gives positive and negative, but it doesn't matter when we have Yemen under modulus. Okay, so put this value in a Yemen. Okay, so we have to put this value in a Yemen. Okay, then we get the value for Yemen as a nx 1 plus n square x square. So we have the value for x, it is a 1 by n. Okay, n into 1 by n, x square which is 1 by n square. Okay, 1 plus n square 1 by n square. Okay, cancel n with n, numerator getting 1. Cancel that n square, numerator denominator it comes to 1 plus 1 which is a 2. Okay, so we got the value for Yemen which is a 1 by 2. That means we got the Yemen non-zero when apply n tends to infinity, and our Yemen test it says that if n tends to infinity Yemen non-zero, then that means our sequence of function not uniformly convergent on our given interval. Okay, that means given it is the real. Okay, or you can take close 0 open infinity. Okay, now this is the Yemen test which says that our sequence of function is not uniformly convergent. Okay, but what happen if we apply the definition of uniformly convergent from the sequence of function? Now let's go for the same example on sequence of function on uniformly convergent by using definition. Okay, now here I have by using definition alternative for that our example. Okay, solution of our example. Okay, so here modulus of fn x minus fx strictly less epsilon, then apply x tends to 0. Okay, so this is the definition of uniformly convergent. It says that modulus of fn x. Okay, fnx which is given here, and fx, the meaning of fx, remember always in our mind. So we always take fx as limit n tends to infinity fnx. Okay, when we apply limit n tends to infinity fnx, we get the fx. So we know that we already found that one, that limit n tends to infinity fnx as a fx which is equal to 0. So this total value strictly less epsilon. Okay, so what is meant by epsilon? Epsilon is the smallest positive integer here. Okay, we always take it as the smallest positive integer. Okay, so modulus of this term is strictly less epsilon. We know that this is the total positive, so modulus removed here. So go for the adjustment of the term from both sides. Okay, so after adjustment of these terms, we get the 0 strictly less epsilon n square x square minus n times modulus of x plus epsilon. Okay, so as we observe here, our this side it's look like a type of a quadratic equation in the term of n. Okay, like ax square plus bx plus c. Okay, so this is the quadratic equation in the term of n, and we have to find out the root of that quadratic equation. Okay, so that root of quadratic equation which belongs to our interval or not. Okay, so here for finding the quadratic equation, root of quadratic equation, we have to always worried about the discriminant. Okay, because discriminant, it is the only value which gives us the value from real or the value from imaginary. Okay, so we always find the discriminant by using this square root. Okay, and we know that for finding the square root of any for finding the root of any quadratic equation, we always use minus b plus minus square root of b square minus 4ac upon twice of a. This is the quadratic for finding the root of quadratic equation, ax square plus bx plus c. Okay, this is the result. Okay, so apply the result here. Okay, minus b, that means minus of minus modulus x, it remain modulus of x, plus minus b square, that means minus modulus x square, it remain modulus x square, minus 4 times a into c. Okay, c it is here epsilon, a it is here epsilon x square, epsilon x square. Okay, because this quadratic equation in the term of n. Okay, so that's why this come like this. Okay, upon denominator 2 times. Okay, so here 2 times epsilon x square. Okay, so here 2 times a means 2 times epsilon x square. Okay, so here we can see that the value for n which is bigger than this one. Okay, why this is bigger than this one? So I choose here. Okay, so we can observe here by using this one. So x is a here part of denominator. Okay, if the x is a part of denominator, that means if we choose any interval, okay, as x tends to 0, that means the interval which contains 0, if we choose 0 as a part of interval, that our quadratic equation here, that the factor of quadratic equation here which contain denominator x square, when x goes to 0 on our interval, we use that interval here, x goes to 0 from our interval, that denominator goes to 0. Okay, so something upon 0, we know that it is infinity. Okay, so if that sequence of definition from sequence of function we consider here smaller than epsilon. Okay, but it gives the factor or a root which goes to the infinity as x contain closed interval 0. Okay, so then we say that the sequence of function which is a not uniformly convergent. Okay, as n x contain as a part of a 0. Okay, so if we delete that 0, okay, if we take away that 0 from our closed interval 0 open infinity, so our sequence of function it gets uniformly convergent. So this is a troublemaker 0 here. So remove that 0, then open interval 0 infinity, it is uniformly convergent, but closed interval 0 infinity, it is not uniformly convergent. Okay, then we say that the x which is equal to 0 is a point of non-uniformly convergence. Okay, so this is the point where our sequence of function it is non-uniformly convergent. Okay, so in our today's lecture we learn for finding the value or for finding sequence of a function whether it is uniformly convergent or not by using two ways. Okay, two methods. First method it is by using Yeoman test, and second method it is here by the standard definition of uniformly convergence. Okay, so thank you everyone, thank you for my today's lecture.